Learning outcomes. After studying this module, you shall be able to know about spectroscopic methods for determination of absolute configuration of coordination complexes. Learn about the spectroscopic methods optical rotatory dispersion and circular diachories. Learn about circular biorefrigerance and cotton effect. Identify the different types of curves obtained in these two techniques. Learn the difference between optical rotatory dispersion and circular diachories. Spectroscopic methods for the determination of absolute configuration of coordination complexes. As we are aware of, the lowest DD transition in hexaamine cobalt 3 complex is 1A1G to 1T1G. Thus, in case of complex tris-ethylene diamine cobalt 3 ion, a very similar electronic transition and visible spectrum is observed. There are two phenomena associated with these DD transitions named optical rotatory dispersion and circular diachorism. These two methods are very useful in determining the absolute configuration of any complex. So, there are two spectroscopic methods of determination of absolute configuration. First is optical rotatory dispersion and another is circular diachorism. These two methods depend on the behavior of polarized light passing through a solution of the optically active compound. The results have to be interpreted by comparison with a similar compound of known absolute configuration. The principles of two techniques are discussed in following sections. Optical rotatory dispersion. The rate of change of specific rotation with wavelength is known as optical rotatory dispersion. As we already know that the plane polarized light can be regarded as an experimentally broken down into two circularly polarized components equal in amplitude but opposite in their senses of rotation. An optically inactive substance will retard the speeds of the two circularly polarized components to the same extent and no net rotation can be observed. However, the speeds of the two circularly polarized components are retarded by an optically active substance to different extents, and this results in the rotation of plane of polarization. When an optically active medium rotates the plane of polarization, this is the result of unequal angles which EL and ER make with Z axis. Rotation of electric field component E, it has been shown that since the speed of light in a medium is manifested in the refractive index of the medium, the essential property of an optically active substance is that it has different refractive indexes for the left and the right circularly polarized light, NL and NR respectively. This is also the reason why an optically active substance is said to be circularly biorefrigerant. Circular biorefrigerance. the difference in indices of refraction for right circularly polarized light and left circularly polarized light is known as circular birefringence. Thus, on passing plane polarized light through optically active compound result in unequal rate of propagation of right and left circularly polarized rays due to circular birefringence. This unequal rate of propagation of both right and left circularly polarized light deviate the plane polarized light from its original direction, and it is called optical rotation. Optical rotation is caused by compound changes with the wavelength of plane polarized light, that means circular birefringence. Optical rotation is measured using a polarimeter. Measuring optical rotation as a function of wavelength is termed as optical rotatory dispersion spectroscopy. Circular birefringence or optical rotation can be calculated quantitatively by using following equations, that are angle of rotation theta per unit length expressed in degrees, which is given by theta is equals to pi divided by lambda NL minus NR, where lambda is the wavelength of incident light, NL and NR are the refractive indices for the left and the right circularly polarized light, and L is the path length in the medium. Multiply this equation by 1800 by pi converts theta lambda to the rotation alpha. Optical rotation alpha is equals to 1800 theta divided by pi. Spectropolarimeters are the polarimeters used to make measurements at a variety of wavelength. They record alpha as a function of alpha at a specified temperature. At a specified wavelength, optical rotation alpha is called as specific rotation, that is denoted as alpha subscript lambda superscript t, and molar rotation m subscript lambda are used. We are already aware of specific rotation alpha lambda, that is equal to alpha divided by L into C, where alpha is the observed rotation at wavelength lambda in degrees, L is the light path in decimeters, and C is the concentration of optically active substance in grams per milliliter. For optical rotatory dispersion, it is more common to use molar rotation instead of specific rotation, and molar rotation is defined as alpha m divided by 100 into L into C, where alpha is the observed rotation at wavelength lambda in degrees, L is the light path in decimeters, C is the concentration of optically active substance in grams per milliliter, and M is the molecular weight in grams per mole. A curve which shows the wavelength dependence of optical rotation is called as optical rotatory dispersion spectrum. ORD curve is a plot of specific rotation alpha versus lambda or molar rotation m versus lambda. The following animation shows what happens when a plane polarized light wave, which is indicated in a light blue color, transverse a medium that does not slow down the left circularly polarized component, which is shown in red color, of a wave at all, but slows down the right circularly polarized component, which is shown in green, somewhat. For the latter component, the refraction index of the material is n is equals to 1.05. We placed an intersecting plane before and after the piece of the material. We show the field vectors at the point of intersection of the light beam and the intersecting planes. The following animation shows that the intersecting planes from the front. On the left, the plane before the material, and on the right, the plane after the material. As you can see, exiting wave continues to be a plane polarized wave. As you can see that the resulting wave continues to be a plane polarized wave, but its plane of polarization is no longer vertical. The polarization plane has rotated by 36 degrees. Optical rotatory dispersion curves. Optical rotatory dispersion curve is a plot of change in optical rotation with the wavelength. This can be classified into two main types, that are plane curves or anomalous cotton effect curves. Plane curves. These curves do not contain any peak or inflection in a curve, and the curve does not cross the zero rotation line. The plane curves are obtained for the chiral compounds which are not having any chromophore. That means these chiral compounds does not have any absorption in the wavelength where these are being examined. Example given: hydrocarbons, alcohols, etc. Usually two types of plane curves are observed: plane positive optical rotatory dispersion curves. Graph A represents plane positive ORD curve. Plane positive ORD curves are obtained when the specific rotation increases with decreasing wavelength. In other words, clockwise rotation is plotted positively. However, plane negative ORD curve. Plane negative ORD curve, graph B represents plane negative ORD curve. Plane negative ORD curves are obtained when the specific rotation decreases with decreasing wavelength. In other words, counterclockwise rotation is plotted negatively. Anomalous cotton effect curves. To understand these curves, we have to first understand cotton effect. The cotton effect is the characteristic change in optical rotatory dispersion in the vicinity of an absorption band of a substance in a wavelength region where the light is absorbed. The absolute magnitude of the optical rotation at first varies rapidly with wavelength, crosses zero at absorption maxima, and then again varies rapidly with the wavelength, but in opposite direction. Each cotton effect consists of two extrema, a geometrical maximum called a peak and a geometric minimum called a trough. The cotton effect is called positive if the optical rotation first increases as the wavelength decreases. That means positive cotton effect curve has its peak at the longer wavelength region, while the cotton effect is called negative if the optical rotation first decreases as the wavelength decreases. That implies negative cotton effect curve is defined as having its trough appear at the longer wavelength. Optically pure enantiomers always display opposite cotton effect or ORD curves of identical magnitude. Optically pure enantiomers always display opposite cotton effect ORD curves of identical magnitude. Anomalous cotton effect curves are obtained for the optically active compounds having chromophore which absorb in near UV region. These curves show the peaks and troughs depending on the present absorbing groups. Thus, they are called an anomalous dispersion of optical rotation. These are again divided into two types: single cotton effect curves and second is multiple cotton effect curves. Single cotton effect curves. These are anomalous dispersion curves which show maximum and minimum both occurring in the region of maximum absorption. So, there are only one peak and one trough in single cotton effect curves. The vertical distance between peak and trough is called amplitude. Amplitude is expressed in degrees. So, molecular amplitude alpha is equals to theta 1 minus theta 2 divided by 100, where theta 1 is molar rotation of trough or peak from the shorter wavelength, theta 2 is molar rotation of extreme peak or trough from higher wavelength. Multiple cotton effect curves. These are little different from single cotton effect curves. Here more than one peak and one trough are obtained. As you can see here, there are more than one peak and one trough in the multiple cotton effect curves. Circular diachorism. Circular diachorism refers to the differential absorption of left and right circularly polarized light. Optically active compounds possess this special property of absorption of left-handed circularly polarized light to a different extent than the right-handed circularly polarized light. This phenomena is called as circular diachorism. The electric field of a light beam causes a linear displacement of charge when interacting with a molecule, whereas the magnetic field of it causes a circulation of charge. These two motions combined result in helical displacement when light impinges on an optically active molecule where both field vectors in a same place are of same direction but at different moments of time. Circular diachories occurs as the wavelength of the incident light approaches that of the absorption band. In this case, the oscillation of charges in the material is damped as energy is removed from the field by absorption process. If the absorption is different for the right and left-handed circularly polarized light, then the linearly polarized light will become elliptical polarized. The elliptically polarized light is shown in purple color, which is composed of unequal contributions of left and right circularly polarized light. The ellipticity theta of the light is defined by the arc tangent of the ratio of the major axis to the minor axis of the transmitted light. Usually, the actual absorption of each component of light is measured and the difference in absorption is called the circular diachorism. The following animation shows what happens when a plane polarized light wave transverse through a medium that does not absorb the left circularly polarized component of the wave at all, but highly absorbs the right circularly polarized component. We placed an intersecting plane before and after the piece of the material, and we show that the field vector at the point of intersection of the light beam the intersecting planes. Here we show the intersecting planes from the front. On the left, the plane before the material, and on the right, the plane after the material. The component shown in red transverse the medium unchanged, and the component shown in green gets fainter, means its intensity decreases to about 36% of the original value. The superposition of the two components is no longer a linearly polarized wave. The resulting field vector does not oscillate along a straight line, but it rotates along an ellipsoid path. Such a light wave is called an elliptically polarized light. Take a closer look and notice that the big axis of the ellipse is parallel to the polarization plane of the original light wave. This is always the case regardless of which circular component is absorbed more by the medium, but the direction of rotation of the elliptically polarized light is determined by the circular component that remains stronger after transversing the material. In our case, the field vector of the elliptically polarized light rotates in the same direction as that of the component shown in red color, which transverse the medium without losing intensity. Of course, it is very unusual for a material not to absorb one circular component at all, but real materials usually absorb both components but to a different extent. it was only for the sake of simplicity that we presented a situation where the material is completely transparent to one of the circularly polarized component. The quantities in CD are delta epsilon, that is difference in molar absorptivity, and theta, that is the angle of ellipticity per unit length. Delta epsilon is equals to epsilon L minus epsilon R, which is not equals to 0, and the angle of ellipticity theta is defined as theta is equals to pi kappa L minus kappa R divided by delta, where tan theta is equals to ER minus EL divided by ER plus EL, where kappa is the absorption index. It is related to the absorption coefficient K by equation K is equals to 4 pi by lambda into kappa, and theta has the unit radians per centimeter. The equation has now same form as the equations for ORD. So, theta can be converted from radians to degree by multiplying it 1800 divided by pi, and K is equals to 4 pi divided by lambda into kappa. So, now theta becomes 1800 into kappa L minus kappa R divided by lambda, which is equals to 1800 KL minus KR divided by 4 pi. Now, the molar ellipticity of the sample is given by theta is equals to theta divided by CL into M divided by 100, where C is the concentration in moles per liter, L is the path length in centimeter, theta is the measured ellipticity in terms of extinction coefficient, where K is equals to 2.303 epsilon into C. The equation can be now rewritten as theta is equals to 2.303 into 4500 epsilon L minus epsilon R divided by pi is equals to 3300 delta epsilon. So, circular diachorism is equals to delta epsilon is equals to epsilon L minus epsilon R. All optically active compounds exhibit CD in the region of the appropriate absorption band. CD is plotted as epsilon L minus epsilon R versus lambda. The difference between the absorption of left and right handed circularly polarized light and is measured as a function of wavelength. CD is measured as a quantity called mean residue ellipticity, whose unit are degrees centimeter square per decimeter mole. CD spectrometers have an optical system much like UV visible spectrophotometers, with the addition of a crystal of ammonium phosphate mounted to allow imposition of a large electrostatic field on it. When the field is imposed, the crystal allows only circularly polarized light to pass through. Changing the direction of the field rapidly provides alternating left and right circularly polarized light. the light received by the detector is compared electronically and presented as the difference between absorbances epsilon L minus epsilon R. An ordinary spectrophotometer can also be used to measure circular diachorism. It is only necessary to provide some means of production of right and left circularly polarized radiation. The spectrum obtained in circular diachorism is almost identical to an absorption spectrum, except that the peaks can be both positive and negative in the case of circular diachorism. These positive and negative deflections in circular diachorism spectrum depend on the sign of delta epsilon or theta and also corresponds to the sign of the cotton effect. Maximum of the CD occurs at the absorption delta max. Summary. In this module, we discussed that there are two spectroscopic methods of determination of the absolute configuration, that are optical rotatory dispersion and circular diachorism. Optical rotatory spectra are dispersive, whereas circular diachorism spectra are absorptive. The two phenomena are related by the so-called Koenig-Kramers transforms. CD plots are Gaussian, however, ORD plots are S-shaped. Positive or negative deflections depend on the sign of delta epsilon or theta and corresponds to the sign of the cotton effect. Maximum of the CD occurs at the absorption lambda max, where more than one overlapping cotton effect are there. The CD may be easier to interpret than the ORD with overlapping S-shaped bands.